The Subtle Magnetic Fields, SMF. The Hidden Tuners of Reality by L.S. Larkey, author of the trilogy Gravity and Creation, theoretical astrophysicist of a new cosmology. My friends, imagine for a moment that you're standing in a quiet meadow at twilight. The gentle hum of cicadas blends with the subtle rustle of leaves in the breeze. You reach out your arm and you can almost sense the Earth's magnetic pull, the intangible force that guides a compass needle north. This familiar magnetism, governed by laws we learn in school, has always seemed both simple and awe-inspiring. Yet behind this everyday phenomenon, there may lie an even deeper realm of possibility. Subtle magnetic fields, or SMFs, that extend beyond the usual forces we know, weaving a hidden lattice through the cosmos and shaping reality in ways we're only beginning to guess at. For centuries, our understanding of magnetism revolved around the elegant ideas set forth by pioneers who distilled countless observations into tidy laws. Those laws revolutionized technology, enabling us to harness electricity, design motors, and interpret everything from planetary fields to electromagnetic radiation. But in our eagerness to celebrate these breakthroughs, perhaps we assumed that we had learned everything essential about magnetic phenomena. After all, magnetism seemed so comprehensively explained, so integrated into the tapestry of modern science, that we rarely questioned whether a more elusive form might be at work alongside the magnetism we measure in the lab. Subtle magnetic fields invite us to entertain the idea that everything we know about magnets and electromagnetic interactions might be just the topsoil of a far deeper layer. The notion suggests that there could exist a richer, more delicate field, permeating not only galaxies but also atomic orbitals, bridging the void that conventional theories sometimes leave unfilled. When cosmologists examine galaxies spinning at speeds that ordinary gravitational calculations fail to explain, or when quantum physicists notice curious shifts in atomic frequencies that don't align with standard electromagnetic theory, these small puzzles might be the footprints of SMFs, a whispering force that has gone undetected because our instruments are tuned only to the coarser aspects of magnetism. One of the most astonishing ideas about these subtle magnetic fields is their potential to exist in higher dimensional or fractal forms. Now, the concept of higher dimensions often conjures images of science fiction, parallel universes, and impossible geometric shapes. But here we speak of higher dimensions or fractal expansions in a different sense, a continuous layering of reality, where scales replicate themselves in patterns that loop and curve. When we peer into a fractal design, we see repetition echoing at smaller and larger magnitudes, each scale a mirror of the next, but with slight variations that produce the complexity of the whole. The hypothesis is that SMFs do something similar, from the swirling heart of a galaxy down to the swirling electrons in an atom. A single principle of subtle magnetism might echo across the range of scales, never truly vanishing, never truly becoming insignificant. In classical thinking, we often treat fields like magnetism as if they fill ordinary three-dimensional space. But subtle magnetic fields may weave themselves through fractional dimensions or hidden layers of existence, quietly adjusting their strength and geometry in response to local conditions. It's as though we have glimpsed only the visible tip of a great iceberg. Beneath the surface, the structure fans out in unexpected directions that standard instruments cannot detect. Perhaps these deeper, fractal pathways are the reasons some magnetic phenomena appear so stable on galactic scales and so nuanced in quantum regimes. In our quest to understand subtle magnetic fields, we encounter what might be called early hints, small anomalies or perplexing observations that signal the presence of something beyond classical magnetism. Take, for example, the spiraling arms of galaxies. Astronomers have observed large-scale fields that seem surprisingly coherent, stretching across regions previously unexplained by typical magnetic dynamo theories. The cosmic rays that zip through these enormous structures also appear to interact with magnetic fields that are unusually extended or stable. Could it be that subtle magnetic fields, existing at a layer deeper than the standard electromagnetic fields, provide the backbone for these galactic-scale patterns? Meanwhile, if we zoom in 1 billion times smaller, down to the domain of atoms, certain laboratory results have hinted at shifts in spectroscopic lines that classical theories struggle to account for. Sometimes, these shifts are small enough to be brushed aside or labeled experimental error, yet they crop up often enough to stir curiosity. It's as if a minor tuning knob is gently shifting an atom's energy states. Traditional magnetism and electroweak forces can explain most such interactions, but now and then the data suggest that something else, a subtle nudge, might be coaxing electrons into slightly altered patterns. What does it mean then to think of subtle magnetic fields as the hidden tuners of reality? Imagine turning the dial on a radio. Each notch on the dial corresponds to a different frequency, a distinct station. Tuning to one frequency brings music, while a small shift can bring static or a completely different station altogether. SMFs, in this metaphor, would be the intangible hand that gently adjusts that dial, ensuring that galaxies orbit without flying apart, or that an atom's electrons settle into stable orbits. In a classical picture, we'd say magnetism is part of electromagnetism, which in turn influences how particles move. But in this broader picture, these subtle magnetic fields seem to orchestrate the cosmic dance in a more pervasive fashion, simultaneously affecting giant cosmic structures and minute quantum transitions. If all this sounds ambitious, perhaps even fantastical, one must recall that many ideas in science have started with anomalies and intangible hints. Quantum mechanics, general relativity, and other theoretical leaps began as attempts to reconcile perplexing data that defied simpler models. The push to investigate whether SMFs exist is similar. Researchers across disciplines keep an open mind, running advanced simulations to see if introducing a subtle fractal magnetism might replicate the real patterns we see in galaxies or the anomalies observed in atomic labs. We might ask, where does a deeper magnetism meet the notion of gravity or the vacuum of space itself? In some frameworks, especially the broader Fibonacci SMFs theory, subtle magnetic fields intertwine with a dynamic vacuum that can push on matter. Normally, we think of space as empty, offering no push or pull except for what mass-based gravity dictates. But there's an emerging perspective that the vacuum is far from inert. It may be alive with fields and fluctuations that, when combined with magnetism, produce effects akin to a cosmic breeze guiding stars in their orbits. From that vantage point, SMFs are not a mere addendum to classical magnetism. They're part of a grand tapestry where space, fields, and matter swirl in fractal choreography. One may wonder, if these fields are so important, why haven't we unequivocally measured them? The short answer lies in how subtle they may be. Laboratory instruments are designed to measure standard electromagnetic fields with extraordinary precision, but they're not necessarily tuned to detect small distortions or fractal expansions that might hide behind the normal signals. It's rather like trying to hear an ultra-quiet bird call when a roaring waterfall drowns out all other sounds. The everyday electromagnetic interactions and quantum fluctuations could mask the faint presence of SMFs. Nevertheless, scientists are beginning to explore next steps. Observationally advanced telescopes might look for unusual alignments in galactic fields, or for structures that cannot be explained by classical theories. In the lab, spectroscopic methods could push into new frontiers, measuring transitions in atoms and molecules to mind-boggling levels of precision, hoping for a telltale sign that something else is at work. The truth is that if subtle magnetic fields are real, they may have existed all along, influencing processes from the cosmic to the microscopic. We have lived alongside them, never realizing how a deeper magnetism could be stitching the layers of reality together. Now indulge yourself in a moment of reverie. Imagine a hidden ocean of magnetism flowing through every atom, every star, and every cluster of galaxies. This ocean might be calm and undetectable to most instruments, yet it shapes currents that guide cosmic evolution and atomic transitions alike. From time to time, a ripple breaks the surface, a small but telling anomaly in an experiment or an observation. Through each ripple we catch a fleeting glimpse of a deeper tide. Such is the poetic allure of SMFs. If there is a fractal or higher dimensional aspect to subtle magnetic fields, one can picture each region of space echoing the conditions of neighboring regions, scaled up or scaled down. The same patterns that swirl in the cosmic realm might reflect themselves in the quantum domain, forming a coherent theme across the entire tapestry of existence. Over time, this fractal design may have guided the birth of structure, from star formation to the assembly of galactic clusters, while also gently nudging electrons to adopt stable energy levels. In effect, the universal story becomes less about chaotic accidents and more about resonant waves that keep matter from spiraling into disarray. The metaphor of cosmic music becomes irresistible. Each galaxy, each atom, a note played in harmonic alignment with these underlying fields. Doubts and skepticism, of course, are inevitable. Many who stand firmly on the bedrock of established physics might argue that conventional magnetism, combined with gravity, plasma physics, and dark matter or dark energy concepts, can account for most cosmic phenomena. They might say that quantum chemistry already explains atomic transitions without needing a hidden field. But even they might concede that odd wrinkles appear from time to time, a rotation curve that fits awkwardly, a spectral line that shifts in an unexpected manner. Could these be the corners in which subtle magnetic fields dwell? Meanwhile, for those captivated by the possibility, the universe takes on a fresh luminosity. Instead of a silent vacuum dotted with indifferent stars, one can envision a labyrinth of fractal paths, an infinite network in which subtle forces remain as crucial as the known pillars of electromagnetism or gravitation. In such a scenario, we become part of a dance, choreographed by subtle magnetic fields, as much as by the more familiar laws, living in a grand acoustic space where most of the instruments have yet to be identified. On Earth, we see only the major frequencies, but the background is alive with hidden harmonies. How might our view of the world shift if these subtle magnetic fields were definitively proven? For one, it could unify phenomena that currently require separate, sometimes awkward explanations. It might present alternative angles on cosmic puzzles, offering elegant solutions that sidestep the need for massive amounts of invisible matter. It might, in the quantum realm, shed light on why certain isotopes are more stable than others, or how slight variations in local environments can trigger unexpected shifts in atomic behavior. And beyond pure science, it could open new technological horizons. Imagine harnessing or tuning SMFs in advanced materials, energy generation, or refined instrumentation that can map reality more completely. Yet for all the future promise, the subtle magnetic fields remain, for now, in the realm of hypothesis, one that stirs the imagination but demands rigorous verification. The best documentaries and explorations will not only celebrate these grand possibilities but also emphasize the need for meticulous, careful inquiry. This is how knowledge grows, from hints to theories, from theories to experiments, from experiments to either triumphant confirmation or the impetus to conceive even better theories. Still, the central idea remains enchanting. That behind every magnet we hold, behind every aurora dancing across polar skies, and behind every spiral galaxy shimmering in the vast night, there could be a deeper magnetism at play. A magnetism that arcs across fractal dimensions, shaping the cosmic ocean we inhabit. A magnetism that might, in the quiet corners of advanced laboratories, tip the scale on how electrons move or how atoms resonate. And a magnetism that, if real, beckons us to reconsider the very nature of reality, reminding us that the tapestry of our universe is woven with more subtlety, more majesty, and more depth than we have ever suspected. And so we stand on a threshold. Subtle magnetic fields may be waiting to be unmasked, offering us a window into the next chapter of physical law. It is a chapter whose words we do not yet fully understand, whose images remain part of speculation, but whose storyline, if proven, could unify some of the most perplexing issues in both cosmology and quantum physics. When we finally tune our instruments, or perhaps tune our theoretical lenses just right, we might detect the gentle chorus of SMFs and see that what we once assumed were separate notes in the cosmic score are bound together by an underlying melody, a deeper resonance humming through every corner of existence. Until then, let us keep our senses open and our minds unburdened by the assumption that we have reached the end of the story. The universe, in its boundless creativity, may always hold more secrets. And subtle magnetic fields, weaving invisibly through galaxies and atoms, might be one of its most astonishing secrets yet, a sign that the horizon of human discovery remains as vast and luminous as the stars themselves.